Welcome to NPTEL course on Fractals and Multifractals. In the last class, we have discussed the how to obtain the fractal dimension for the any non-empty compact subset on a metric space X, and we have used the geometric sequence, then thereby we obtained the fractal dimension of the set A given in the metric space X. Now we are going to discuss how to obtain the fractal dimension of the object in R power n more precisely, because the last theorem we proved for the general metric space. Now we are going to more precisely on R power n. For that, let us discuss or let us recall what is the definition of fractal dimension. Let A be the given set in H of X and H be any metric space. For each epsilon greater than 0, we can find the minimum number of boxes required to cover the set A. Then taking the limit of ratio between logarithm of number of ball over the size of the boxes of radius epsilon. If this limit exists, we can call it the fractal dimension A. Now, this theorem says let A belongs to H of R power m, where R power m is the collection of all m tuples x1, x2 up to xm, such that all xi's are member of R, order m tuples. This R power m forms the metric space with respect to the Euclidean metric, which we already discussed. Now, for covers R power m by closed square boxes of side length 1 by 2 power n. Cover this R power m, the space R power m, by closed square boxes of side length 1 by 2 power n. One can ask how to cover the R power n by the boxes of size 1 by 2 power n. The pictorial representation is given here. Consider this space. Now, consider this is the box size of power 1 by 2. Then, if you are increasing 1 by 4, 1 by 2 power 2, then this will be come to like here. Then box size of side length 1 by 2 power n. Here we are taking n as 2, that means R power 2, then we are covering by 1 by 2 power n, m as 2, or here R power 2, that means m equal to 2. In R power m we are taking m equal to 2 and n equal to 2, that means R power 2 power 4, R power 2 power 2 is 1 by 2 power 2. Here, for if you are consider the unit box, if you are consider this unit box 0, 1 cross 0, 1, this box 0, 1 cross this 0, 1, we are taking 1 by 2 power 2 as the side length. So, we need 4 boxes in the side, 1, 2, 3, 4 boxes covers this unit square. Likewise, we can cover by using this box, this box throughout the R power 2, throughout the R power 2. Likewise, if R power m is given, we can cover R power m by closed square box of side length 1 by 2 power n. Let n of A denote the number of box of side length 1 by 2 power n. So, side length usually the n of number of boxes required to cover the object A with the closed ball size epsilon, we are denoting n of A comma epsilon. Here side length is 1 by 2 power n we are taking, therefore, this notation we are providing n of A, that means side length n denote the number of boxes of side length 1 by 2 power n which intersect the attractor, If d equal to limit n tends to infinity, the logarithmic natural log of n of a over ln of 2 power n, then d is called the box counting or fractal dimension of a. That means we are finding the fractal dimension of object A in R power a subset of R power m by using the counting the boxes. Therefore, we naming it as a box counting. Whereas in the previous definition, we are taking X as the arbitrary metric space and n of a comma epsilon denote the closed ball. It can be any closed ball, but here we are precisely taking the boxes. Therefore, this technique is called the box counting. So, this D is called the fractal dimension by using boxes. So, D is called the box counting dimension of A, or equivalently we can call it the fractal dimension of A. Now, let us prove this theorem. We observe that for m equal to 1, 2, 3 and etc., 2 power minus m times n minus 1 is less than or equal to n of a comma 1 over 2 power n less than or equal to n of k of n for all the n 1, 2, 3, where here k of n is the smallest integer k satisfying this inequality. K is greater than n minus 1 plus 1 by 2 log 2 m. Now, we are squeezing this one by this 2 quantity. Now, we are squeezing this element by this 2 quantity. Then, the first inequality hold this inequality. The first inequality hold because a ball of radius 1 by 2 power n can intersect at most 2 power m on grid boxes of side 1 by 2 power n minus 1, that is here 1 by 2 power n minus 1. The second follow from the fact that the boxes of side S can be fit inside a ball of radius r provided r power 2 greater than or equal to this finite series S by 2 power 2 plus S by 2 power 2 up to m times S by 2 power 2 equal to m times S by 2 power 2, because we are taking r power m element by the Pythagoras theorem. Now, limit n tends to infinity. First, we can find the n k of n over ln 2 power n, which is equal to ln 2 power k of n over ln 2 power n times this quantity. Since k of n over n tends to 1, this is nothing but d. This is nothing but d. For the second one, now you can come to the second inequality. Limit n tends to infinity, ln 2 power minus m n minus 1 over ln 2 power n equals ln n minus 1 over ln 2 power n minus 1 when limit tends to infinity, n tends to infinity, which is equal to d. Now, from the theorem 1 which we discussed in the last class, if you are taking the epsilon n as c r power n, in which if you are taking r equal to 1 by 2, then this theorem comes true, because the both the side is this quantity ln n minus 1 over ln 2 power n minus 1 goes to d, and this quantity ln n k minus 1 over ln 2 power n goes to d. Therefore, this quantity is the equal to d. We are finding this one converges to d, this one after taking limits converges to d. Therefore, this one will converges to d. In this theorem, there is nothing magical about using boxes of side length 1 by 2 power n in this theorem. One can equally well use boxes of side c times r power n, where c is greater than 0 and r lies between 0 and or any fixed real number. We can use the box side length as this one, then still this theorem is valid. maybe the sketch of the theorem is given here. One can understand here from this sketch. This is the theorem statement. We are taking A belongs to H of R power m, and we are covering R power n by closed square of boxes of side length 1 by 2 power n. That cover is shown here. Here we are covering 1 by 2 power n. We are taking here as n equal to 2. We are taking n equal to 2. Then let n of A denote the number of boxes side length 1 by 2 power n with intersect the attractor. If D satisfying this one, D obtained from this limit, then D is called the box counting dimension or fractal dimension of A. This is the theorem statement. For this one, first we form this n of A of 1 by 2 power n for all n equal to 1, 2, 3. Then we are choosing k of n by satisfying this one. You can observe for this quantity, this inequality, the first inequality hold because of a ball of radius 1 by 2 power n can intersect at most 2 power m on grid boxes of side 1 over 2 power n minus 1. Here you can take this picture, here to here you can compare. This is 2 power m boxes, this is 2 power n boxes. So one can understand this one, this quantity is less than this one. And similarly for this property, this inequality, the second follow from the fact that a boxes of side S can fit inside a ball of radius R. This is the ball of radius R. This is the ball of radius R. Radius. Boxes of side S. This is the box with the side length S. Each length is S. This box can fit into the circle of the radius R. Therefore, R square is greater than this sum of this quantity, which is equal to m times S by 2 power 2. By Pythagoras, one can get this one. Now, limit n tends to infinity, ln of n k of n over ln 2 power n equals ln of 2 power k of n over ln of 2 power n, which times ln of n of k n over ln of 2 power k of n, which is equal to the D. Because this one tends to 0, sorry, k of n over n tends to 1, not 0. This quantity n of k of n over 2 power k of n, which gives this result D. So, this is the sketch of the proof. Now, we will find the fractal dimension of an object by using this theorem, box counting theorem. So, now we need to take the element from R power n. So, let us consider the metric R power 2 in Euclidean with the Euclidean metric. Let A belongs to X. This is our metric space X, and take an element A belongs to X. Let A equal to singleton element A, singleton set A. Then fractal dimension of A equal to 0. For proving this one, you can see the set A consisting of a single point in the space. We have the R power 2. In R power 2, we have only the singleton point here A. The set consisting of a single point in the space like this one. This is our set. This is the only one point. Now, for each epsilon greater than 0, the number of boxes required to cover A equal to 1. For example, if we have this is only one point. This is our set. This is our A equal to singleton A. For each epsilon greater than 0, any epsilon greater than 0, number of boxes required to cover A with epsilon radius is equal to 1, because any positive epsilon you can take this as center, then you can get this. But if you take any positive epsilon, then it will cover this one, easily it will cover. So, the number of boxes required to cover with the single point is 1. Then you can see what is the from here one can understand what is ln of n of a comma epsilon over ln of 1 by epsilon. For any epsilon, this is number of boxes required to cover the set is A is 1. So, ln 1 is 0. So, you will get the fractal dimension of an n, a singleton set is 0. Now, this is a just trivial example. In R power 2, if we are taking the singleton set, the fractal dimension is 0. It is a trivial example. Now, we will find some other interesting results. Consider the metric space R power 2 with Manhattan matrix. Here in R power 2 with Euclidean metric we have taken. Here we are taking R power 2 with the Manhattan matrix. Let A consisting of the line segment 0, 1. Then the dimension is 1. See, we have the straight line segment 0, 1 in R power 2. In R power 2, consider this line segment. Then the number of boxes required to cover A, this n of A comma epsilon denote the minimum number of boxes, closed boxes of radius epsilon needed to cover A. We are taking not a Euclidean metric, Manhattan metric. In the Manhattan matrix, balls have a diamond shapes. However, along with the x axis, they behave like a interval of length 2 epsilon. See, we are taking this Manhattan metric. If it is an Euclidean metric, then for covering this interval, we can take any point x here, then x minus epsilon, x plus epsilon you can take. By varying different epsilon, we can cover this interval 0, 1. We can take epsilon in anywhere, but if you are taking here and move here and there, change the different epsilon, we can cover this closed interval 0, 1. So, this is like we can cover like this different thing we can cover. Whereas now we are taking Manhattan matrix. In the Manhattan matrix, the balls have a diamond shape. It is explained here. What is the Manhattan matrix? First of all, Manhattan metric is in the, if we have the 2 points x1, y1 and x2, y2, then Manhattan matrix is x1 minus x2 plus y1 minus y2. This is the Manhattan matrix. Now, the closed ball of radius epsilon centered this point x naught and y naught, because we are taking the point in R power 2. Ball of radius epsilon center x naught comma y naught, in our case we will denote like x naught comma y naught, the point and the epsilon radius is defined as set of all points x comma y such that this distance must be less than or equal to epsilon. So, if you are taking x naught y naught here, then the distance between x naught to, if you are taking the epsilon, then x naught plus epsilon is here, x naught minus epsilon is here, this is our y naught, this is our y naught. Then y naught is here, then y naught plus epsilon is this side in upper side and y naught minus epsilon is this side. Now, we have these 4 points. In this 4 point, if you want to find the Manhattan distance, it is like a square, like this one, because the distance function is given here. So, the balls are look like a diamond shapes. Intersects the ball with the x axis, just you can intersect the ball with the x axis. Now, you will get, you just intersect this one with here, then here you will get x minus x naught minus epsilon, here x naught plus epsilon, this form one can get. So, the total length of this one, total length means x naught plus epsilon minus x naught plus epsilon, this will cancel, you will get 2 epsilon, the interval of length 2 epsilon. Now, if you want to cover closed interval 0, 1 with the closed ball of radius epsilon, each ball contribute an interval of length 2 epsilon on the x axis. If it is your interval 0, 1, if you want to cover this closed interval by a ball with radius epsilon, each balls look like this diamond shape, then each ball contribute the interval of length 2 epsilon. This will contribute 2 epsilon, this will contribute 2 epsilon, this will contribute 2 epsilon, and so on. Also this will contribute 2 epsilon in the x axis. Thus we need about 1 by 2 power epsilon such intervals. Therefore, the number of boxes required to cover A with the radius epsilon is directionally proportional to 1 by 2 epsilon up to the constant factor. Now, for let epsilon greater than 0, then it is quite easy to see that the number of balls required to cover A with epsilon, we can choose like this one. The integer part of the this function is the integer part of the real number. So, minus 1 by epsilon you can take, then integer part of minus denote the number of boxes required to cover the n of A and epsilon. In the following figure, the graph of ln of number of boxes n, that means the ln of n plotted with ln of 1 by epsilon, it is given here, that ln of 1 by x and it is ln of the integer part of 1 by x is plotted here. It is like a step function. Now, for computing the fractal dimension, one usually evaluate the limiting slope of the discontinuous function. Now, you can see despite rough start, it appears clearly that the limit epsilon tends to 0, ln of n of A by epsilon over ln of 1 by epsilon equal to 1. From this figure one can understand it is equal to 1. Now, in fact, if you are taking epsilon in between 0 and 1, epsilon and 0 and 1, then ln of 1 by epsilon equal to ln of 1 by epsilon equal to 1 less than or equal to. Instead of this one can use, if you are using this one, then this quantity less than or equal to this quantity, then this is nothing but number of boxes required to cover A with radius epsilon in Manhattan metric. Now, this quantity is less than or equal to ln of 1 by epsilon plus 1, because we are taking the integral part, this number plus 1 which is less than or equal to this part. Now, this one can write ln of this one 1 plus epsilon over epsilon. So, one can write this as ln of 1 plus epsilon plus ln of 1 by epsilon. This we can write here. Now, both the sides here convergence to 1 as epsilon tends to 0. If epsilon tends to 0, you can see this quantity is ln of 1 by epsilon, this is ln of 1 by epsilon. If epsilon tends to 0, this quantity tends to infinity, therefore, this quantity will become 0. 1 by epsilon, if epsilon tends to 0, 1 by epsilon will get larger, therefore, ln of the large number will get infinity. So, 1 by this one we can get 0, this one equal to 1, whereas this side also 1. Therefore, this quantity must be equal to 1, the middle quantity, again by the squeezing property, we can say this one also convergence to 1. So, we conclude that the fractal dimension of closed line segment is 1. Now, we are finding for finding the fractal dimension of A, we are using the boxes of length epsilon. This type of box we are using. Now, first one we can discuss with the trivial example. Second one we started with the r power 2 with the Manhattan matrix. Now, let x comma d be a metric space. Here it is a random metric, not r power 1 or r power 2. A comma b, c R belongs to the member of X and A is the consisting of 3 number A, B, C, D, the finite set, we need to show that the fractal dimension is 0. It is easy that A, this is a finite set which contain in X. If R, if you are choosing minimum among the distance between any pair of these 2 points, then choose epsilon as less than R by 2. That means if you have 3 points like this one, A, B, C, maybe randomly, not in the straight line also, C, anywhere, you can find the distance between A and B and C and A and C you can find. Choose the minimum among all the numbers. Suppose this is the minimum number, assume that this is the minimum number R, then choose epsilon as less than R by 2. Then if you are drawing the closed ball with respect to this epsilon radius, with this center one can get this type of closed ball and one can get this type of closed ball. We can distinguish all this point. Therefore, the number of boxes, minimum number of boxes required to cover this 3 point is 3. Then you can see limit epsilon tends to 0, this quantity is constant ln 3 over ln of 1 by epsilon. Whenever this epsilon tends to 0, this quantity will get larger, therefore the total limit will converge to 0, therefore the fractal dimension of the set A equal to 0. The fractal dimension of, that means one can understand that the fractal dimension of point set or the singleton set A, which we discussed in the first example, it is 0. The fractal dimension of the line segment which we are discussing 0 to 1 is 1 with respect to the Manhattan metric we discussed, keep in mind, in R power 2. So, now as of now we have discussed the some sets in Euclidean space or the R power n with the smooth object, the set finite set and the singleton set which is also finite set and the line segment. If we are finding the fractal dimension using the box counting theorem, whether it is 0 for the finite set and the countable set, finite set, whereas in the countable set is also it is equal to 0, and for the line segment we are finding the box counting dimension which is equal to 1. Now we have to find the box counting dimension of our well known fractals by using this box counting theorem. So, as we already discussed the classical example as Cantor set, Von Kashkar and Sierpinski triangle, let us try to find the box counting dimension, that means the fractal dimension using the box counting theorem in the next class. Thank you. This is a reference book.